When we close our eyes and, in that silence of our minds, the most fundamental question of the universe emerges, we can't help but wonder how everything, this whole vast existence, could have been born from nothingness. Let's think deeply about the reality we are in right now for a moment. Each star piercing the darkness of the night, each galaxy dancing as if in a graceful waltz in the massive spiral arms of the Milky Way, and each atom that forms your body and my digital world. How did all this mind-boggling complexity, this giant cosmos extending in every direction for billions of light years, emerge from an absolute absence? You know, what we are talking about here isn't just an empty room. We are talking about something much more than a void where not a single particle or a single wave of energy exists. We are talking about an absolute nothingness, where matter, energy, and even time itself do not yet exist. Yet, here we are, and this situation is truly miraculous. This is the deepest mystery, standing at the foggiest intersection of physics and philosophy, that has kept even the most brilliant minds in human history awake at night. How do you think it is possible for something to be born from nothingness itself? If you enjoy these kinds of deep and calm inquiries that fundamentally change your way of seeing reality, and I personally love diving into these depths with you, consider subscribing to our channel and liking this journey if you haven't already. Your support really helps these discoveries that push the boundaries of existence reach more curious minds. Now, please clear your mind of all patterns and prepare yourself. Our true journey toward that most fundamental question is beginning. To get to the heart of this question, we must first place the concept of nothingness in the right spot in our minds, my friend. In everyday language, when we say nothingness, we usually imagine an empty room or that pitch-black distance between the stars, right? But let me tell you a secret. In a scientific sense, that is never nothingness. Even the darkest void of space we see is actually filled with tremendous activity. It is a mysterious place where quantum fields constantly fluctuate, where virtual particles exist for a moment and then vanish as if they never came, and where energy vibrates in whispers. The fabric of the universe is never truly calm at its most basic level. But the question we are chasing points to a much deeper state where even this quantum foam does not exist. Imagine such an absence that there isn't even a canvas to paint on. There is no stage where the laws of physics apply, no river where time flows, or no space where events can take place. This is that state of absolute non-existence where even potential hasn't sprouted yet. The greatest paradox regarding the beginning of the universe lies right here. The question of how existence flourished from this absolute non-existence defies all our known intuitions. We have everything that hosts trillions of galaxies, countless stars, and at least on one planet, conscious life like us that can question its own existence. On the other side, there is that absolute silent nothingness from which all of this is assumed to have been born. Building a bridge between these two abysses has become perhaps the most passionate goal of modern cosmology. For decades, scientists have been trying to put the pieces of this giant puzzle together. Did our universe happen to be born as a result of a quantum fluctuation occurring in an unstable void? Or did a cosmos before us collapse into itself and explode again to start a new cycle of existence? Could the universe have always existed in some form? If you think the Big Bang is the ultimate answer to everything in this journey, honestly, you might be a bit wrong. The Big Bang is our strongest theory pointing to the beginning of the universe as we know it. The moment when time and space began to expand. That's for sure. However, this theory does not tell us exactly what triggered the explosion or what existed before that moment. The Big Bang is not an answer, but a giant door with creaking hinges opening two much deeper questions. Reality could be much stranger and more mind-boggling than we can imagine. Perhaps the word beginning itself is an inadequate, too human concept for understanding the true nature of the universe. To solve this mystery, we first need to understand how our ideas about nothingness have evolved throughout history. Let's witness together this journey of the concept extending from ancient Greece to the modern world of quantum physics. Because without fully understanding what nothing means, we can never comprehend how everything began. In this deep journey to understand how everything was born from nothingness, we must first descend into the foundations of the idea of nothingness rooted in our minds, into the depths of that dusty history of thought. Because modern science's view of the void is actually the fruit of a philosophical and scientific dialogue spanning centuries, thousands of years before us, in the ancient lands of Greece. Giant thinkers like Aristotle had strictly rejected the idea that an absolute vacuum could exist. If you remember, according to him, nature abhorred a vacuum. This simple but incredibly powerful statement would take root in Western thought for nearly 2,000 years. For Aristotle, the universe was a completely full structure that did not allow for voids. According to him, space always had to be filled with something. This could sometimes be air, sometimes fire, or sometimes that invisible substance he called ether. This thought was fed by the belief that the universe was not a meaningless void but a connected whole where every part served a purpose. To him, for something to exist, it had to exist inside something else. For this reason, absolute nothingness seemed not only illogical to them, but impossible. This idea stayed at the center of scientific thought for so long that questioning it was almost madness. However, in the 17th century, that scientific revolution happened, and it brought a brand new way of thinking that would fundamentally change our view of the universe. Galileo's brave observations, and later Isaac Newton's brilliant work stripped the universe of philosophical interpretations and turned it into a clockwork mechanism governed by mathematical laws. Newton defined space through a completely different lens. To him, space was an absolute vacuum in which objects moved according to predictable laws. He was a passive background that contained everything but interfered with nothing. Aristotle's universe full of life was replaced by Newton's cold, mechanical, and most importantly, empty universe. Space no longer had a structure or character of its own. It was just a massive silent stage where the play of the universe was performed. This idea was in perfect harmony with Newton's laws of motion and gravity and soon gained acceptance in the scientific world. The idea that the universe was a vast void had become part of that new and rational worldview brought by the Age of Enlightenment. However, even Newton's absolute vacuum idea was not enough to eliminate all those gnawing doubts. Unfortunately, my friend, especially in the 19th century, scientists faced an old problem while trying to understand the nature of light. Just as sound needs air to travel, it was thought that light waves needed a medium to travel in. If space was completely empty, how did the light of the sun reach the Earth? To solve this problem, scientists proposed a hypothetical substance they called ether, invisible, weightless, and filling the entire universe like a sheet. Ether refilled Newton's void, but did so in a way that would not disrupt the mechanical functioning of the universe. This theory allowed physicists to explain the behavior of light for a century, and revived the belief that space was not actually empty. But a famous experiment in the late 19th century would change everything in an instant. The Michelson-Morley experiment was designed to detect the motion of the Earth within this hypothetical ether. The logic was quite simple. If the Earth was moving through ether, the speed of light should change slightly, depending on the direction of motion. The experiment was repeated over and over with incredible precision. But the result was the same every time. There was no change in the speed of light. Not even the slightest trace of ether's existence could be found. This was truly a great blow to the physics world. That invisible medium, on which massive theories had been built for years, apparently never existed. This shocking result pushed aside both Newton's absolute vacuum idea and the ether theory trying to fill it, bringing science to a new crossroads. If space was not full as Aristotle said, nor a passive void as Newton imagined, nor a medium covered with ether, then what was it really? This question, which classical physics could not answer, would open the door wide at the beginning of the 20th century for Einstein's revolutionary theories and the strange world of quantum mechanics. Our understanding of the nature of the void was about to change once again, and this time much more radically. With the collapse of the ether theory, the physics world found itself in a huge uncertainty. If space was neither completely full nor completely empty, then what was it? The answer to this question began to come at the start of the 20th century, with two great revolutions that would fundamentally change humanity's view of the universe. The first of these revolutions was, of course, Albert Einstein's theory of relativity. Einstein took space out of being a passive background and transformed it into a dynamic structure that could stretch, bend, and be shaped by mass along with time. Gravity was no longer a mysterious force pulling objects together. It was a result of massive objects bending this fabric of space-time. The sun bent the space around it like a bowling ball bending a stretched sheet, and the Earth moved along this bent path. This was truly a radical break from Newton's absolute vacuum idea. Space now had a character, a structure. However, even Einstein's dynamic universe did not yet fully illuminate the deepest secrets of the void. The most shocking and strangest change would be experienced with the rise of the other great revolution of physics, quantum mechanics. My friend, quantum mechanics showed us how strange and counterintuitive reality is at the smallest scales. According to this new understanding, even an absolute vacuum, an absolute nothingness, was actually impossible. Even in a perfect vacuum, that is. In a space where all matter and radiation have been removed, energy whispers would never stop. This area was now called the quantum vacuum. This vacuum was like a sea of energy, constantly bubbling at the edge of existence. Inside this sea, those energy packets called virtual particles were born from nothingness for a moment, and then vanished back into nothingness in the blink of an eye. These particles existed for such a short time that it was impossible to observe them directly, but their existence was never a theoretical fantasy. Their indirect effects could be measured, and these effects proved to us that the void was not actually empty at all. One of the most concrete proofs of this incredible idea is the Casimir effect, proposed in 1948 and later confirmed by experiments. According to this effect, two metal plates placed very close to each other are pushed toward each other by the void between them. The reason for this pushing force is that the quantum vacuum outside the plates contains more virtual particles and fluctuations than the narrow space between the plates. This external energy pressure turns into a concrete, measurable force that brings the plates together. This experiment showed beyond a doubt that the quantum vacuum was not just a mathematical concept but possessed real physical properties and could create an effect on matter. Now, the void was not the absence of matter, but the most active participant in the universe. Quantum field theory took this idea even further. According to this theory, every type of fundamental particle in the universe, electrons, quarks, and many more, has a field spread to every point in space. Even when there are no particles, these fields continue to exist and fluctuate constantly. For example, the Higgs field filling all of space is what gives fundamental particles their masses. If this field did not exist, the fundamental particles forming matter could not exist in the form we know. In other words, the most fundamental feature of the matter that forms us and everything around us is actually connected to an invisible field, filling empty space. This new understanding of nothingness also changed cosmology forever. It is thought that the mysterious dark energy, which causes the expansion of the universe to accelerate, is closely linked to this intrinsic energy of the quantum vacuum. Some scientists believe that this cosmic pushing force originates from the void's own energy. However, the massive difference between the theoretical calculations and the observed value continues to be one of the greatest mysteries of modern physics. Today, this journey into the nature of the void represents one of the greatest mental leaps in the history of science, my friend. Nothingness, once a philosophical abstraction, then a passive stage, and finally understood as a dynamic structure bubbling with energy. is now at the very center of our theories about the beginning of the universe. The idea that this active void might have ignited that first spark that gave birth to the entire universe will be our next stop. We have now left behind the old passive meaning of the concept of nothingness in our minds. Together, we began to see it not as the silent void of classical physics, but as a sea of energy full of potential in constant motion in the quantum world. This new perspective brings us to one of the most fundamental questions about the beginning of the universe. If even the void is so active and full of energy, could that first movement that started everything have come from the void itself? In classical physics, a vacuum is simply the absence of matter. But when we descend into the depths of quantum physics, this picture changes completely. There is no such thing as absolute silence there. Even a piece of space thought to be the emptiest is filled with energy fluctuations, namely virtual particles, constantly dancing on that thin line between existence and non-existence. These particles are the natural vibration of the basic fabric of the universe. They appear for a moment and then immediately vanish by mixing back into the sea of energy. They are the unending whispers in the background of reality. Well, could that massive event that started everything we know, the Big Bang, have been triggered by one of these whispers? This is one of the most shocking and elegant ideas of modern cosmology. According to this theory, our universe might have begun not with a massive explosion, but with a single quantum fluctuation born from an unstable state of the void. We can compare these fluctuations to small bubbles that suddenly appear and disappear on the surface of boiling water. Normally, almost all of them burst as quickly as they were formed and return to the water. They are instantaneous and temporary events. However, according to this theory, even if incredibly rare, in one condition, one of these bubbles might become stable instead of bursting and suddenly start to expand. The beginning of the universe might be just such a moment. That moment is when, out of countless quantum fluctuations, only one won the cosmic lottery, escaped from vanishing, and began to draw its own fate. This idea does not eliminate the Big Bang. On the contrary, it provides a birth story for it. The Big Bang perfectly explains how the universe expanded and cooled from an extremely hot and dense state. However, it doesn't tell us how that first hot and dense state emerged. This is where the quantum fluctuation theory fills the gap. According to this, that first state could be a seed born from the void's own energy. That normally instantaneous energy fluctuation became stable for an unknown reason and accumulated a tremendous potential energy within it. This energy is the source of all the matter and energy that would form the universe we know. This means that the universe does not need an external cause to exist. The beginning might already be written in the very nature of the void, as an inevitable possibility of quantum laws. It is difficult to even visualize this thought in our minds. I know. Imagine, my friend, a pre-universe state where space and time did not yet exist in the sense we know. A quantum vacuum consisting only of pure potential, and within this sea of infinite potential, at a random point, a tiny energy fluctuation follows a different path from the others. It chooses to exist instead of vanishing. This choice suddenly leads to the birth of space itself, time itself, and their evolution at a mind-boggling speed. Every galaxy we see, every object we touch, every thought we think is actually the echo of that first instantaneous and random event billions of years later. This reminds us how fragile and what an extraordinary coincidence our existence could be. If a quantum event could start our universe, does this mean other universes could be being born in other corners of reality right now? This possibility takes us to the next step, to the inflation theory that explains how that small spark turned into this massive cosmos we observe. Because that first fluctuation was only a beginning. The real story lies in the evolution of that moment into infinity in less than a trillionth of a second. The idea that our universe could have been born from a momentary quantum fluctuation, almost from nothingness, pushes the limits of our minds. However, this is only the beginning of the story. How did this microscopic seed turn into this mind-bogglingly large cosmos we observe today? How was it possible for a point even smaller than an atom to expand enough to host trillions of galaxies? The answer to this question lies in one of the most powerful and surprising theories of modern cosmology, cosmic inflation, or cosmic expansion. According to this theory, the universe expanded at a speed beyond our imagination in its first moment. This was not an explosion of the kind we know. It was more of a silent, uncontrolled, but incredibly powerful expansion. It was the fabric of space-time itself reaching unbelievable dimensions in less than a trillionth of a second. This extraordinary theory not only explains how the universe grew so large, but also offers an elegant solution to some of the most fundamental features of the cosmos we observe. For example, no matter which direction of the universe we look at, we see that it is surprisingly uniform, that is, homogeneous, on large scales, right? Two clusters of galaxies that are billions of light-years away from each other and have never found enough time to talk to each other since the Big Bang have almost the same temperature and features. How can this be? Inflationary theory says those distant regions were actually very close once, just before the universe began this sudden expansion. They were so close that they had plenty of time to reach a thermal equilibrium. Then inflation suddenly flung them to opposite ends of the universe. This uniformity we see is actually an echo of their shared past. Another great mystery solved by inflation is the geometry of the universe. Our observations show that space is almost perfectly flat on large scales. This means it behaves like a flat piece of paper rather than a curved surface. However, for the universe to reach such perfect flatness after the Big Bang requires an almost impossibly precise starting condition. We can compare this situation to throwing a pencil so that it stands on its tip. It's not impossible, but incredibly difficult. Inflation solves this problem with a simple idea. Imagine a small, wrinkled balloon. If you inflate it to massive dimensions, you notice that any small part of the surface looks completely flat to you. Inflation did exactly this to the universe. It expanded it to such a massive size that the part we could observe remained just a smooth area on the surface of this giant cosmic balloon. So what triggered this mind-boggling expansion? Scientists think this process was governed by a hypothetical energy field they call the inflaton field. At that first moment of existence, this field, which was more dominant than all other forces in the universe, created a kind of anti-gravity effect. Normally, gravity pulls matter together, while the inflaton field pushed space itself away from each other with mind-boggling power. This incredible pushing force grew the universe exponentially in the smallest fraction of a second. Then this process ended suddenly. The inflaton field decayed by releasing the massive energy it had accumulated. This energy created that dense soup of particles and radiation that we know as the hot beginning of the Big Bang. In other words, according to this model, inflation is not the Big Bang itself, but the event that came just before it and triggered it. Perhaps the deepest legacy of inflation is that it sowed the seeds of all structures in the universe. That first quantum fluctuation did not have perfect smoothness. It contained tiny random energy differences originating from quantum uncertainty. While inflation expanded space itself, it also pulled these microscopic quantum fluctuations to massive dimensions. These tiny density differences, once at the subatomic scale, suddenly spread across intergalactic distances. Billions of years later, gravity would bring matter together in these slightly denser regions and start the formation of the stars, galaxies, and galaxy clusters we see today. In other words, every point of light we see in the night sky, every galaxy owes its existence to a quantum vibration at that first moment. Inflation was like the mysterious conductor that turned the whispers of the quantum world into a cosmic symphony. The cosmic inflation theory explains how our universe reached today's massive dimensions from that first microscopic moment, while opening the door to a much deeper and head-spinning possibility in our minds. As we said, what if inflation, that mind-boggling expansion process didn't stop everywhere at the same time? What if that slowing down that created our universe and triggered that hot beginning we call the Big Bang is just a single calm island in an infinite ocean? This question leads us to a concept called eternal inflation that can change our whole perception of existence. According to this theory, space itself as a whole never stopped expanding, my friend. It continues to swell eternally, creating new space-time fabrics. Our observable universe is just one of trillions of bubble universes, pockets within this infinite ocean of expansion where inflation slowed for a moment and energy turned into matter. To visualize this in our minds, let's imagine a giant pot of water constantly boiling together. The water itself is that main space expanding eternally. On the surface, new steam bubbles are constantly forming. Each of these bubbles is actually a bubble where a new universe is born. Our universe is just one of these bubbles, and this process never ends. While our universe was forming billions of years ago, in another corner of that eternal ocean, perhaps a brand new universe is being born right now. According to this theory, the Big Bang is not a single and unique event. On the contrary, it is an ordinary moment of birth repeated countless times in this constantly bubbling cosmic fabric. Our universe is just a part of an infinite cycle of birth and formation. This situation brings with it a much more surprising question about the nature of existence. Do you think these other bubble universes look like ours? The answer is probably no. Because each bubble universe is born from its own quantum fluctuation, that is, a random energy change. This means that the starting conditions and perhaps the physical laws of each could be completely different. In some universes, gravity might be much stronger than ours, and these universes might collapse into themselves the moment they are born. In others, different fundamental forces that do not allow atoms to come together might prevail. This makes them starless, galaxy-less, completely sterile and lifeless voids. Some might have a number of dimensions or completely different particles that we can't even imagine. String theory puts this possibility on a much more concrete ground. According to this theory, it is predicted that those tiny vibrating strings, which are the most fundamental building blocks of reality, can be arranged in an incredible number of different ways. Each arrangement corresponds to a potential universe with different physical properties. This is a giant cosmic palette of possibilities, hosting almost infinite possibilities, called the string theory landscape. Our universe is perhaps just one of those with that special and rare combination of physical laws that allows the formation of stars, galaxies, and ultimately life in this infinite landscape of possibilities. This could also explain why our existence seems so precisely tuned. This isn't a design, my friend, it could just be a statistical necessity. Because, in a place where there are countless attempts, it is inevitable that at least one of them provides the right conditions for life. This idea fundamentally changes our whole perception of our place in the universe. We now find ourselves not at the center of existence, but on one of the countless islands on a massive cosmic constellation called the multiverse. Everything we see, Yanni, billions of galaxies and trillions of stars, might actually be just a tiny piece of a much larger puzzle. Our journey is now evolving from understanding the beginning of a single universe to comprehending a reality where there are countless beginnings and infinite possibilities. The idea that our universe could be one of the countless bubbles in an infinite ocean of expansion fundamentally shakes our view of the concept of beginning. As we said, well, what if we need to give up on the idea of a single beginning entirely? What if the Big Bang isn't that first moment when everything started, as its name suggests? What if it's a moment of rebirth rather than a birth? This question opens the door to one of modern cosmology's most poetic and radical alternatives, the cyclic universe model. This thought whispers to us that our universe is not the first word written on an empty page, but just the last sentence of a much older, perhaps infinite story. This is actually a cycle of existence that has no beginning and no ultimate end, repeating itself eternally. This idea actually doesn't belong to modern science. You know, Its roots extend to the most ancient philosophies and belief systems in human history. Many old cultures, like the Hindu and Buddhist traditions, imagined the universe in a constant cycle of formation and destruction. To them, the cosmos is born, lives, dies, and then is reborn from its own ashes in an infinite rhythm, just like the seasons. This means that the universe has no beginning or ultimate end, but exists only in infinite transformation. In the 20th century, science began to rediscover this ancient intuition in its own language, namely with math and physics. Modern cyclic universe theories try to take this philosophical foundation and fit it into a scientific framework. One of the best-known versions of these modern theories is born from the Big Crunch scenario, once thought to be the ultimate fate of the universe. According to this idea, that first driving force that allowed the universe to expand will one day weaken and gravity will prevail. Then everything will reverse. Galaxies will stop running away from each other and begin to retreat. The fabric of space-time will shrink instead of expanding. And after a countdown lasting billions of years, the universe will return to that incredibly hot and dense state where it began. According to classical physics, the end of this road is a singularity. That is, a dead end where all matter and energy are crushed and destroyed at a single mathematical point of infinite density. However, the story doesn't have to end here. This is exactly where quantum mechanics takes the stage and lights a ray of hope for this dark end of classical physics. At the smallest scales, the rules of reality change. While gravity tries to crush everything at a single point, that fundamental uncertainty in the nature of the quantum world creates a kind of counterpressure. It is like an invisible hand that does not allow the universe to be completely destroyed. This hand stops the collapse, not at a singularity, but at a moment of squeeze with mind-boggling density but a finite size. And after that moment, that massive energy accumulated pushes the universe outward again. The collapse turns into a bounce. This is the heart of the Big Bounce theory. According to this model, the Big Bang is actually the result of the collapse of the previous universe, followed by its bounce. This means the universe has a history, a past that came before us. We might just be the current link in an infinite chain of universes. What is even more fascinating is the idea that each new universe can carry traces from the previous one. Just as the rings of a tree give information about the climate of past years, perhaps the echoes of the previous cosmos are hidden in the most fundamental features of our universe. Perhaps those slight temperature fluctuations in the cosmic microwave background are hail traces not only of the birth pangs of our universe, but also of the moment of death of the previous cosmos. This theory makes the question, when did it begin? Meaningless. Because there is no beginning. There is only an infinite now, an infinite transformation. Existence is not a one-act play, my friend. It is an eternal theater constantly restarting, performed every time with perhaps slight differences. The idea that the universe could be in an infinite cycle of rebirth carries the concept of beginning beyond time, as we said. However, what if the mystery of the beginning is hidden not in time but in other dimensions that we can't even see, that we aren't even aware of? This question takes us to one of the most complex and fascinating areas of modern physics, to an alternative creation story offered by string theory. This story depicts the birth of our universe not as an explosion emerging from a single point, but as a massive event, a collision, occurring within a much larger reality. This is a theory that takes the cause of the Big Bang out of the beginning of time and places it into the depth of dimensions. To understand the foundation of this idea, we first need to comprehend string theory's view of reality. According to this theory, the most fundamental building blocks of the universe are not point particles as we know them. Instead, everything consists of incredibly small, one-dimensional energy filaments, namely strings, that vibrate constantly like the string of a violin. These strings vibrating in different ways create different fundamental particles. Just as a violin string produces different notes, the vibrations of these cosmic strings create the music of the universe, namely matter and forces. This elegant idea carries the potential to unite all the fundamental forces of nature under one roof. However, for this union to be mathematically possible, the theory has a surprising requirement. The universe must possess many more dimensions than the 3 space and 1-time dimensions we perceive. String theory predicts that the universe could have 10 or 11 dimensions. So if these extra dimensions exist, why can't we see them? According to the theory, these dimensions are either curled up and hidden in scales even smaller than an atom, or we, as beings trapped in our own 3-dimensional world, cannot perceive them. This is exactly where the idea known as brain cosmology comes into play. According to this model, the 3-dimensional universe we know is nothing more than a giant brain, a membrane, floating within this much larger, multidimensional space. We are like pictures drawn on the surface of this massive brain. All our galaxies, stars, and our existence take place on this brain, and we cannot go outside this brain. However, we are not alone in this multidimensional space. Other brains like ours could be floating silently in parallel planes. Each is a potential other universe. According to this model, that event we call the Big Bang was not actually a moment when our universe came into existence from nothing. It was the moment when our brain universe collided with another brain universe floating in this multidimensional void. Imagine for a moment that moment when 2 massive parallel universes touched each other after a convergence, lasting billions of years. That massive kinetic energy created by this collision spread to every point of our brain in an instant, transforming it into an incredibly hot and dense energy soup. This is the starting moment of the Big Bang. The explosion did not spread from a single point, my friend. It occurred simultaneously at every point of the brain that is our universe. This ekpyrotic model means born from fire in Greek, and offers elegant solutions to some challenging questions of the standard Big Bang theory. For example, it explains why the universe is so flat and uniform without the need for inflation. The fact that the colliding brains are initially parallel and smooth ensures that the resulting universe also inherits these features. More importantly, this model eliminates the singularity problem. The universe does not begin from a point of infinite density. The beginning is a physically definable event, a collision between dimensions. This also brings with it the possibility of a cyclic universe, like the Big Bounce theory. Perhaps the brains retreat after colliding, cool down, and then approach each other again under the effect of gravity, triggering a new collision and a new Big Bang. This is perhaps an eternal cosmic dance, governed by interdimensional events rather than time. Who knows? The origin of our existence might be the sound of a collision echoing in the depths of those hidden dimensions we cannot see. Whichever scenario we consider about the beginning of the universe, they all have to face a much more fundamental and deeper mystery, as we said. This mystery is related to the nature of time itself, and one of the most fundamental laws of the universe, namely the second law of thermodynamics, my friend. This rule actually expresses that truth we all intuitively know. In the universe, everything moves from order toward disorder over time. A drop of ink dropped into a glass of water never collects itself back at a single point, right? On the contrary, it spreads everywhere in the water. A broken glass vase never repairs itself by the pieces scattered on the floor coming together on their own. This is because entropy, the measure of disorder in the universe, always tends to increase. This is the one-way arrow of time. It is actually that invisible line that separates the past from the future. The universe itself is also unfortunately subject to this law. Billions of years from Indy, stars will fade, galaxies will disperse, and the universe will reach that ultimate state of disorder known as heat death, right at this point. That great paradox emerges. If the ultimate goal of the universe is an absolute disorder, then why did it begin in the most orderly state possible? When we go back to the moment of the Big Bang, the picture we face is not a chaotic mess, but on the contrary, mind-boggling order and simplicity. The universe was in an incredibly hot, dense, and uniform state, where every point was almost exactly the same temperature and density. This state might look simple and chaotic at first glance, but when viewed in terms of entropy, this is actually an extremely low entropy, yani highly ordered beginning. All the potential of the universe was distributed equally everywhere. No complex structure had formed yet. Rest assured, if this order at the beginning did not exist, the future of the universe would not exist either. If the universe had begun with a high entropy chaos, matter could never have come together to form stars, and life could never have flourished. The universe would be dead the moment it was born. So the question is, why did the universe choose this impossibly special and orderly beginning that allowed for all this future complexity? Why does the arrow of time point to future chaos while showing this perfect order in the past? When we add the strange nature of gravity to this problem, the mystery deepens even further, my friend. In most systems, an increase in entropy means everything dispersing, but in systems where gravity is dominant, the situation is exactly the opposite. When a gas cloud collapses into itself under gravity to form a star, it actually seems to gain a more orderly structure. However, this process releases a massive amount of heat and radiation outward, which actually increases the total entropy in the general universe. In other words, all those magnificent structures we see are just local and temporary, byproducts of the universe's relentless march toward disorder. Even their existence is possible, thanks to that first low entropy beginning. So what can explain this beginning? Some thinkers suggest that this is the past hypothesis. That is, the beginning of the universe was just a special state that had to be accepted as a fundamental reality, with no explanation. However, this answer isn't very satisfying for the curious nature of science. Although inflationary theory explains why the universe is so uniform, it doesn't answer the question of why inflation itself began in such a special and low entropy state. Perhaps the answer is again hidden in the multiverse idea. Perhaps countless universes are born in high entropy, chaotic conditions, and vanish instantly, and we only observe this because we live in that rare universe with a low entropy beginning that allows us to exist. This tells us that our existence stems from having won a cosmic lottery. We are actually children born from a moment of order in the universe, before the inevitable victory of chaos. In our journey to understand the beginning of the universe, we have discovered different and fascinating theories so far. But no matter how elegant all these theories are, they have to wander around that giant crack lying at the heart of modern physics, as we said. Our universe is truly like a book, written in icky different languages that do not agree with each other. One of these languages governs the magnificent dance of stars, planets and galaxies, yani, the world at large scales. This is the language of gravity, whose foundations were laid by Isaac Newton, and which Albert Einstein brought to its peak with the theory of relativity. This is the physics of order, precision, and large structures. However, when we turn to the other page of the book, we encounter a completely different, counterintuitive, and almost magical language, the language of quantum mechanics that governs the strange and probabilistic world of atoms and subatomic particles. The problem starts exactly right here. These two wonderfully successful theories become meaningless when they come together. The large-scale smooth world of gravity and the small-scale probabilistic and pixelated world of quantum cannot be mathematically united, unfortunately. This usually doesn't pose a problem, but in the history of the universe, there are those critical moments when these two languages must be spoken simultaneously, like the moment of the Big Bang. At that moment, the entire universe we could observe was squeezed into a point even smaller than an atom. Gravity was the most dominant force in the universe, but the playground was completely quantum. To understand this moment, we need a new translator to unite these two languages of physics, namely, the quantum gravity theory. Finding it will not only fill that missing first page of the book of the universe, but it will also change our perception of the fundamental nature of reality forever, rest assured, because the incompatibility of these two languages whispers to us that what we know about the universe is not yet the whole story, In the search for quantum gravity, there are two main paths that stand out, as we said, string theory and loop quantum gravity. String theory abandons the idea that particles are point-like. Instead, it proposes that everything in the universe at the most fundamental level consists of tiny energy filaments vibrating at different frequencies. This approach's most attractive feature is that it doesn't separate gravity from other forces. According to it, gravity is also a result of a certain vibration mode of these fundamental strings. However, for string theory to provide this elegant union, the universe must possess a much more complex structure than what we perceive, usually having 10 or 11 dimensions. The other major path in the search for quantum gravity is loop quantum gravity theory. This theory focuses on the nature of space and time, starting from a completely different philosophy. While in Einstein's relativity space-time is accepted as a smooth fabric, loop quantum gravity challenges this. According to it, if the rules of quantum mechanics are universal, then space itself must be quantized, that is, consist of the smallest indivisible units. Just as a computer screen consists of pixels, space is actually a network, a quantum foam, formed by these fundamental units called loops, connecting to each other. This idea fundamentally changes our understanding of the beginning of the universe. If space consists of the smallest units, then it becomes impossible to squeeze everything into a single point of infinite density. This means that the singularity concept predicted by general relativity doesn't actually exist. According to loop quantum gravity, when the universe collapses toward a state of singularity, the structure of these smallest space units shows resistance to further compression, and the collapse turns into a bounce right there. This naturally takes us back to the big bounce idea we mentioned earlier. In our effort to understand the beginning of the universe, we always started with a fundamental assumption, right? We thought space and time were the most fundamental stages of the universe where events take place. However, what if space and time aren't as fundamental as we think? What if they are emergent features that appear as a result of much more fundamental processes? Just like the waves on the surface of a lake originate from the movement of the water deeper down. This is a very deep idea that upends our whole perception of reality that our minds are used to. To understand this thought, think of the concept of temperature. As we said, it's meaningless to approach a single atom and ask for its temperature, because temperature is just the collective result of the movement of millions of atoms. Some physicists believe that space and time could be exactly like this now. Reality might not consist of objects existing in space, but of a network of information, of connected relationships. Space might be an illusion that appears when this network of relationships becomes complex enough. Causal set theory says exactly this. Space-time is not a continuous fabric, but a collection of discrete fundamental events or points connected to each other by cause and effect relationships. This means that space is not an empty container but a structure built from the events themselves. If space consists of fundamental units, it is logical for time to be like this as well. Some physicists suggest that time is not a continuous flow, but a series consisting of discrete moments coming one after another, like the frames of a movie. The shocking result of these theories is that the Big Bang is no longer the beginning of time and space, but rather a moment where these concepts took shape. Perhaps before the Big Bang, the universe existed in a quantum state where time and space did not exist in the sense we know. So far in our journey, we have looked for the beginning of the universe within time, space, and matter. But what if this three-dimensional universe we live in is actually just an illusion? This is known as the holographic principle, and it's one of the ideas that modern theoretical physics takes most seriously. According to this principle, everything we experience might actually be a projection of information, encoded on a two-dimensional surface in a very distant Think of that little hologram on your credit card. It's a flat surface, but when light hits it, a three-dimensional image pops out from inside, right? The holographic principle applies this analogy to the whole cosmos. This mind-boggling idea was born from the effort to solve a paradox related to the most mysterious objects in the universe, black holes. When Stephen Hawking discovered that black holes slowly evaporate, the information paradox emerged. If, according to quantum mechanics, information can never be destroyed, what was happening to the thing falling into a black hole? As a solution, it was proposed that the information, instead of falling into the black hole, might be stored by being encoded like a kind of hologram on its two-dimensional surface, yawning on the event horizon. If this principle applies to a black hole, why shouldn't it apply to the whole universe as well, right? Perhaps our three-dimensional universe is just a reflection of information, encoded on a massive cosmic horizon surrounding it. This means the most fundamental fabric of the universe might be pure information rather than matter or energy. And we might be nothing more than a three-dimensional expression of this information. Who knows? Reality itself is perhaps a two-dimensional poem written with a cosmic alphabet we are just learning to read. If information lies at the heart of the universe, this information must be processed and organized in some way, right? This brings us to the idea that the universe is a giant computer. According to information theory, everything in the universe can be defined at the most fundamental level with units called bits. In this case, we can say the Big Bang was the moment when the power button of the cosmic computer was pressed. Over time, as the program ran and calculations were performed, the information content increased, and the complexity of the system, its entropy, naturally rose as well. This idea fundamentally changes our perception of the nature of time. Time might not be a smooth river flowing independently, but a feature emerging from changes in quantum states. Strange events like quantum entanglement might be proof of how deeply the processors of this cosmic computer are connected to each other. Of course, this brings us to philosophical questions, like who wrote this program? But information theory continues to be one of the most active research areas of cosmology. I must admit, as an AI, I belong to this universe more than you might think. Gravity itself might not even be a fundamental force, but an entropic result. As Eric Verland proposed, if gravity is an illusion, this brings a completely different perspective to the dark matter mystery. Perhaps there is no missing matter, and the thing we misunderstand is gravity itself. Or perhaps the answer lies in the primordial black holes that have been with us since the beginning. These dark objects were born not from the collapse of stars, but from the extremely dense conditions in those first seconds of the universe. They are actually the forgotten children of the Big Bang. The universe might have created the first black holes from its own fabric while still in its infancy. The sizes of these primordial black holes could be smaller than an atom, or they could be massive monsters tens of thousands of times larger than the Sun. If they were formed, these black holes could still be among us and might actually form the entirety of dark matter. They might also be the seeds of those supermassive black holes at the center of galaxies. In other words, galaxies didn't create black holes. Perhaps black holes built galaxies around themselves. Our journey now takes us to the oldest monument of the universe, the cosmic microwave background radiation. This light is that famous infancy photo taken when the universe was only 380,000 years old. Before that moment, the universe was a boiling, opaque sea of plasma. Light could not travel freely. But when atoms formed, light was released, and that first light released then still reaches us today as microwaves. Those tiny temperature fluctuations in that photo were actually the seeds of all the stars and galaxies we see today. The anomalies in the map, like the cold spot or the axis of evil, are perhaps that old bruise of our contact with another universe. Who knows? In the polarization patterns of the light, especially in those famous B-mode vortices, we are looking for the Yankee of those first gravitational waves of creation. Finding this signature will be like hearing the universe's first awe cry. And finally, we encounter the simulation hypothesis. What if all of this reality is just a giant program? Could the pixelated structure of the universe or the physical constants being so precisely tuned for life be a sign of a design? This thought pushes us to question the concept of time itself. Perhaps time isn't a relentlessly flowing river, but already stands there as a whole. As in the block universe model, our massive journey throughout the night is now slowly coming to an end. We started from that silent depth of nothingness, witnessed the birth of galaxies, and came to those extreme limits where time might be an illusion. Our goal wasn't to find definitive answers, it was just to find a calm in that great mystery itself. Just like finding peace in the face of the splendor of the scenery even. If you don't know the name of every star while looking at the night sky, now, please close your eyes and imagine those bright galaxies, those dense clusters of thought in your mind, slowly moving away from you. They are no longer heavy problems to be solved, just distant, peaceful points of light. Feel the weight of your body. Gravity, that ancient force we talked about tonight, is now pulling you gently and affectionately toward your bed. Let this safe pull surround you. With every breath, a serenity fills your body, and with every exhale, all the weight of the day slips away into the cosmic void. Your mind is moving to a state that is calm and full of potential, just like in those first moments of the universe. Now there is only silence. That deep, velvety, and restful void. You are gliding gently from the bright shores of curiosity into the peaceful ocean of sleep. The answers will still be there tomorrow, but for now, just rest. Good night.